Faraday, Faraday, you leave me breathless. Do. Okay, what we're going to look at here is Faraday's law. Now, if you haven't watched the AP Physics 2 video on inductance for electromagnetism, you need to go and do that now before you come into this. Because what we're going to do is we're going to take those intro ideas of what is inductance and how we can induce a current and an EMF, and we're going to expand on that with Faraday's law. Okay, and we're gonna drive it kind of from scratch here. Okay, so if you haven't done that, go do that now and then rush back here. I'll put a link in the bottom of this video so you can go back and do that. Okay. What I'd first like to just talk about is something you did last year with mechanics. You know that work is equal to a force dotted with some displacement vector. And maybe you call this delta x, maybe just call it x, maybe you call it f dot d, whatever. But this is some displacement vector, right? Now, I could also write this as the integral of the force dotted with some path vector, okay? Because that's what this is. This is the path, and because I'm taking the dot product of it, I'm only going along the path. So the force along this path will equal the amount of work, okay? That's the true definition of work right there, this integral form. And if you're doing AP Physics C mechanics, you will hopefully have seen this because it pops up on your test. So let's take a look at this equation, the integral of the force dotted with the displacement vector. Well, if I'm talking about E&M, electricity and magnetism, let's think about force real quick. We know that force can be thought of as a charge multiplied by some electric field vector. So let's try that. F equals QE. And then since that E is a vector, I could still dot this with ds, and that will have to equal the work, which is kind of cool. Now imagine for a second we take some charge and we move it in a circle. Well, if we took and you're starting to see a pattern here, if we take a closed path integral of this displacement vector, well, that's just the length of a circle, or the circumference of the circle. So we can just call this ds of 2 pi r. So I get QE times 2 pi r, and that has to equal the work. Now, work can be thought of as a potential energy, U. And if we divide that potential energy per unit charge, that will give us instead a voltage, which is a EMF. So we can actually say here that an EMF can be equal to E times 2 pi r, which we could also write if we wanted to as, and more formally we will write as, we can say that the EMF, whoops, poorly drawn, the EMF is equal to this closed path integral of the electric field dotted with some path vector. Now the really cool thing about this is if we go back and we consider what we know about induction from the AP Physics 2 class in that first intro video, we know that EMF equals something else. We know from Faraday's law that EMF also equals the negative change in magnetic flux divided by some amount of time, or a more calculus way to write this would be the opposite of deflux dt. And remember, this negative here, this is a Lenz's law. That's just a right-hand rule issue, and convention tells us which direction that current go. It opposes the change of flux. So this right here, wing, that is Faraday's law in a complete, more calculus form. And what we see about this is, in the big piece here, is that some closed path integral of the electric field will equal a small differential change in flux in an amount of time. That's the big piece right there. And in the end, that does give us some EMF that we're looking for, or that we might have in that situation. Now, a kind of weird thing about this, if you're kind of looking at this, you might notice that, hey, if we take this particle from before and we walked it in a circle, its beginning and ending positions were the same, which means that its displacement was 0. So the amount of work done should have been 0 there. And you'd be right. In a case like this, we know that the work here is 0, which means that the closed path integral E dot ds is also 0, which means that there would be no change in flux. But that doesn't make any sense because there has to be a change in flux for an induced scenario. And what this means is essentially that if we have induction, the idea of an electric potential, some EMF, that doesn't really apply in the world of an induction. It's not really a good thing to think about. We could use that kind of idea back whenever we talked about electrostatics, because when we did electrostatics, none of our charges were moving. They were static. They were simply there. Once these charges are moving, such as a current, now we get all these induced things here. We start generating B fields and things get wonky. So it's not really a good idea to think about an EMF when we're talking about induced EMFs or magnetic fields in that regard, or just moving charges. It's mainly like a statics thing we like to think about in order to use those, okay? So just kind of a weird little piece there. But this is what we need, and especially this equation here, as we're going to start seeing in our next couple videos coming up. We're going to start looking at some ideas of more magnetic flux, flux linkage, and what we can do with inductors, which will turn out to be things like solenoids. Okay, so for right now, this video will be finished. In our future videos, we'll start breaking down some more of the individual components that we might see in induction problems, and how we can use this Faraday's law and this equation here for some larger expanded problems. Okay, but until next time, adios, and y'all take it easy.